The purpose of this lecture is to provide a way to convert all the information carried by an homomorphism into numbers. In order to do that, we'll have to fix a choice of basis of the domain and the codomain. The direct consequence that the image of a basis determines an homomorphism is that just finitely many numbers are necessary to determine an homomorphism between finite-dimensional vector spaces. All these statements have been proven and covered in the previous lectures 9.3 and 9.2. In this lecture we will see how to produce these numbers from any homomorphism and use them to determine the images of vectors of the domain. The idea is to read the key information carried by an homomorphism. What we read must be converted in numbers in order for us to use mathematics on it, no matter what the elements of the domain and the codomain of the homomorphisms are. Remember that vector spaces can have elements that sometimes are n-tuple of numbers, but other times can be just anything. As long as the set has algebraic structures on it, it can be a vector space. But I stress the fact that in this case I'm talking about numbers, so I want to replace, in a sense, the homomorphism with a set of numbers which they will allow me to recover all the information carried by the homomorphism, which means that using these numbers I will be able to find the image of any element in the domain, in the vector space domain, through this homomorphism. When we have the numbers to recover the images of vectors in the domain, we need the same basis we have previously chosen. So let's sum up all this discussion in the following diagram. On the left, we have an homomorphism from the vector space V to the vector space W. We convert all the information contained in the homomorphism to numbers by fixing two bases, one Vj in the domain and another one which we call Wi in the codomain. Once we have converted the homomorphism in numbers, in order to recover the homomorphism itself, we just need the same basis again. So from these numbers, using the Vj's and the Wi's, we will be able to recover the homomorphism, which means being able to find the image of an arbitrary element in the domain. Let f be an homomorphism, dimension of the domain be finite, n, and dimension of the codomain be finite, k. Fix two bases, one in the domain, Vj, and another one in the codomain, Wi. Point 1. We have shown in lecture 9.2 that f is completely determined by the n vectors that are the image of the basis Vj. So once I have fixed the n vectors f of Vj in W, I have completely determined the map F. Vectors in W can be anything, so I'm not here making any assumption on V, on the elements on V, nor those on W. So to convert these data into numbers, we need to use basis of W. Basis can be seen as a way to convert data concerning vectors in an arbitrary vector space in numbers. What is the conversion? The conversion is I take any vector in a vector space, I express it in function of a chosen basis, and since this is a basis, I will get a unique linear combination to express this vector in function of the basis. While the coefficients of this linear combination will certainly be numbers. The elements of the vector space can be anything, but the coefficients of the linear combination will certainly be numbers. So we can see the basis in W as a way to convert information of the elements of the vector space into numbers. So let's take the image of the first vector of the basis of V, f of V1. Well, being an element of W, it will be a linear combination of these bases that we have chosen of W, the Wi's. And therefore, there is a linear combination of Wi's with certain coefficients, which are certainly numbers. Now, how do we how do we represent these coefficients? Let's call them with the letter A, and certainly they will have one index, which will be running with the index of the element of the basis Wi. However, there is also there must be something denoting the fact in the writing of the coefficients, something that refers to the index of the vector of which we are looking the image. In this case, it is V1, so there should be something here indicating that these coefficients are relevant to the image of the vector V1. So the most straightforward way to do this is to implement a double index notation in which we deliberately chosen to have the first index running with the Wi and the second index running with the Vj's. The image of F2 will be something like summation for I that goes from 1 to k of the Wi's, and according to the convention that we just adopted, the coefficients will be named A, I, and then number 2 referring to the fact that we are looking at the image of V2. And we keep doing this for all the vectors in the domain until the last one, that is Vn, its image will be a linear combination for I that goes from 1 to k of A, I, N, Wi. As it happened in the past, the numbers that we obtained depend on two indices. So it makes perfectly sense to write them as a matrix, but provided that these may be helpful, or else it will be just an added complication. When we take numbers and we make a matrix out of them, it certainly is like adding structures to these numbers, and so it is an added complication to them. And like anything in life, an added complication makes sense provided that this complication will be useful in future. Definition: the matrix A, F, Vj, Wi. This notation explicit three variables on which the matrix A depends. So this matrix A will depend on the homomorphism F, on the basis of the domain Vj, and on the basis of the codomain Wi. We define this matrix to be the matrix whose coefficients are the Aij. This matrix is called the associated matrix to F with respect of the basis Vj and Wi, since they appear in the notation. Notice that this matrix indeed depends by the three arguments F, Vj, and Wi. So the matrix depends on F because, of course, if I change homomorphism, the other homomorphism is different from F, certainly the action on Vj's will be different, because if the action is the same on a basis, then the two homomorphisms coincide, as we have seen. So the action will be different on Vj's, The images, therefore, will be different, and linear combinations in function of wi will be different. Therefore, the matrix will change. If I let f and wi fixed and I change the basis on the domain, I'm looking at the image of different vectors in the domain. So it might happen that the images are different, therefore the matrix will be different. And also if I change just the vectors in the codomain, then, well, since these coefficients are derived by taking the images of the basis and finding linear combinations in function of the wi, changing the basis wi will change the linear combinations, and therefore these coefficients will change. Now, step 2, how do we recover f from this associated matrix to f? So now we see why it is indeed helpful to collect the numbers aij in a matrix. Take any vector little v in the vector space V, and we want to determine its image from this matrix and the basis vj and wi. How do we do that? So first we express v, the vector v, as a linear combination of the basis vj. That will be unique. We can derive these coefficients lambda j uniquely associated to v and to the choice of basis. We write lambda j as a column vector. It will be a length n column vector. The coefficients of the column vector that we obtain taking lambda and multiplying it on the left by the associated matrix, we call them mu1, mu2 through mu k. Notice that the associated matrix is a matrix that has as columns the coefficients of the linear combinations of the images of vj. Therefore, the length of the columns is the dimension of the codomain W. And the matrix A will have dimensions k by n. So the associated matrix will be a k by n matrix. These can be multiplied on the right by a vector of length n, and the result will be a column vector of length k. These coefficients mu1 through mu k are used to compute the f of v. F of v is indeed equal to the linear combination of wi multiplied by these very coefficients mu I that we obtain this way. Let's sum this up quickly. To find the image of a vector v from the associated matrix, we first have to express the vector v in the domain as a linear combination in function of the basis of the domain. This procedure allows us to replace v, which can be anything, an element is just an element of a set, with numbers, namely the numbers lambda j. We assemble these lambda j's vertically, making a column vector of length n, because n is the dimension of the domain. So we replaced v, in a sense, with this column vector, with these numbers. Now, to find the image of v, we take this lambda vector and we multiply on the left by the associated matrix. We are using this matrix is associated to f, but read with the basis vj and wi. This plays a fundamental role here. The basis vj and wi are fundamental. So it's like we take the replacement of v, we multiply on the left by the associated matrix, and what do we get? We get another column vector, which is in a sense the replacement of the image. The image will live in W, the elements in W can be anything, but we can produce from this column vector, so from this number, we can produce precisely the element in W by means of the basis wi. Taking the combination of wi with coefficients mu I allows us to define an element in W that happens to be precisely the image of V through F. Notice that we use the matrix product structure here, and this motivates having given the structure of matrix to the number Aij. Just a moment ago, we were wondering whether it was useful to see these Aij's as a matrix. Well, here is the reason why it is useful. Basically because the action of V can be recovered as left multiplication of the vector that replaces the vector of which we want to find the image. And if we had not collected the numbers Aij's in the matrix form, we could not use this kind of algebraic structure to describe the image of V through F. One last remark of the lecture. Given any k by n matrix B, is it possible to find an homomorphism, say FB, going from a vector space V of dimension n to a vector space W of dimension k, such that the associated matrix of this homomorphism, through the choice of any given basis Wj and Wi equals to B? Well, the answer is yes. For example, for Vn equals to Rn, so we are looking at a particular case of an n-dimensional Euclidean space, and Wk, again, another k-dimensional Euclidean space, and Vj being the canonical basis of the domain, and Wi the canonical basis of the codomain, the definition of Fb is particularly easy. Let F be defined as the map going from Rn to Rk, which takes a vector of Rn. We see it as a column vector, and we multiply on the left by B. We will end up with a k column vector, a k-dimensional column vector, which of course then lives in Rk. And one can easily show that left multiplication by B is an homomorphism, so it is linear. We immediately verify that the associated matrix of Fb with respect of the canonical basis that we have chosen before is precisely B. This is an extremely useful remark, because, as we've seen before, we can recover the homomorphism F from its associated matrix, in a sense, by left multiplication of the matrix. Once we use the basis to change the aspect of the elements of the domain and the codomain, we change their aspects to column vectors, so to numbers, and then we can multiply on the left by associated matrix. Vice versa, any matrix can be seen, in this case we call it B, any matrix B can be the associated matrix of an homomorphism for any given choice of basis of the domain and the codomain. So we fix the basis of the codomain, the domain and the codomain. We can find an homomorphism between V and W that will have that associated matrix with respect of this choice of basis. And here is an easy example, an easy particular case of how it works.